See, I was thinking. It goes up, yeah, it goes up to
In this class on Tuesday, when I had gone through the slide set and I realized I was only halfway through, I thought, wow, I'm behind. Then I went back and looked at my original schedule and was like, wow, I gave 2 days to do this. So if I seemed perplexed when I got to the end of class and seemed a little distraught because I thought I was going slower than I'm supposed to, and right on track. So if you didn't notice that there was any thing wrong with me, then just ignore everything I just said. Kind of like so this particular section. Made a statement in there about the value of Q, and I questioned whether it was true or not because it seemed at the time opposite to me. As it turns out, it is not. What was written in there is true because I was equating it to a table in an inappropriate fashion. Q is more like a probability of something occurring, and I looked up and found the Q rule, which has nothing to do with Star Trek: The Next Generation. And the Q continuum. No clue on that. All the nerds in here got me, but the rest of you are. Say product degeneration rate decreases by a constant factor when the storage temperature is lowered. So this states it the reverse that I did, that it increases for every 10-degree increase, and it would go in line that if you refrigerate something or freeze it or something, that it would slow down the degradation, and that's one of the purposes for refrigeration or freezing. So the typical value of Q is set at either 2, 3, or 4 for most reasonable activation energies. And those activation energies in that one table would show activation energy of about 12.2 or something like that, equated out to a Q of 2, and the 24.3, the highest one, equated out to a Q of 4. That's kind of...
All right.
The Daleks are attacking. That's for you, Dr. Who. Love it. Sorry, I'm a Star Trek or a science fiction nerd from way before maybe your parents were born. I don't know. So a Q10 value of 2 provides a conservative estimate, whereas a Q10 value of 4 is less conservative. So Q of 2 is considered probable, a Q of 4 is considered possible, so it's kind of relatively speaking. So the way it was stated, the larger the value of Q, then this was the slide. So and I can post these two, well, this slide you already have, but I'll post the extra slide for you as well. I didn't until now simply because I didn't want it to be confusing. So assumes most drugs have a energy of activation about 20. And so the statement about shelf life that had the Q, and I thought I had repeated. It was this one. So the lower the Q10 value, the more stable it is. The larger the Q10 value, the less stable it is. As opposed to activation energy, the higher the activation energy, the more stable it is. But don't misinterpret as I did. No, I'm faster than a computer can take. Where I had that table equating this. That's not a literal thing that a Q of 10 means it's got an energy of activation there. That means that it's more likely that we're talking about a reaction that's in that activation energy, but it doesn't actually absolutely equate to it. So I can guarantee you I won't ask you a question of what Q value corresponds to what energy of activation value, because that's misleading. Yes.
I'm kind of confused in what the definition of Q is.
Q is another way on top of the Arrhenius relationship that stability can be predicted based upon accelerated steps. And Q is calculated for each 10-degree change in temperature. You can go in either direction, either higher or lower. If you're doing an accelerated study, you're going higher, which is why I presented it the way I did. All right, we were talking about various and sundry types of reactions. Remember, parallel and combination and series and those types of things as they relate to drug stability. And we used the Arrhenius relationship and Q10 values in order to predict stability in advance of having real-time data. The types of reactions that can be involved in drug degradation are a variety. We're going to go over some of the most common ones and how we can, to a certain extent, limit their impact. What we can't do outside of one of you inventing a stasis prescription container in which time stops is stop degradation or prevent degradation. We can slow it down, but we can't stop it. So drug is going to degrade, but we can put it in a situation to make it slower than possible. We can change the conditions to a certain extent. So types of degradation reactions that we'll look at, very common: hydrolysis, oxidations, dimerizations, isomeric changes, photodegradation, conformational changes, and just outright chemical incompatibilities. You obviously, in that case, if a drug is very acidic, you would not put it in a very basic environment, because then you would have a nice acid-base reaction that would inactivate it. So hydrolysis. Definition of hydrolysis: breaking molecular bonds through a reaction with water. Most common in formulations where water is present. So in compounding, the stability of a compounded product that has water tends to be much less than things that don't have water in it. The vast majority of liquid preparations that we make will have water in them, simply because other liquids, I guess you could make, well, and it has happened. You will likely hear at some juncture that, have you heard of sulfa drugs? Anti-infective agents, sulfa agents. When those first came out back in the 30s and 40s, they were thought miracle drugs, but they were very insoluble in water. Very difficult to make a liquid preparation for them. And they were made in combination. There were triple sulfa compounds that had 3 different drugs in them. So those were made, since they didn't dissolve in water, one enterprising company thought, I found the solvent that they would dissolve in. It's propylene glycol. which is the significant active ingredient in antifreeze. So the sulfa compounds dissolved nicely. The patients, largely pediatric, took them, and there were a number of deaths from ingesting what amounted to antifreeze. Obviously, not a good, viable solution to that. It was a nice, elegant product, but didn't do what it said. That's one of the things that resulted in one of the initial laws about drugs, and that initial law was the company has to prove that their product is safe. So up until then, they didn't. And it wasn't until about 30 years later, in the 60s, with the Durham-Humphrey Act, that companies actually then had to prove that their product was effective. So now they have to prove that it's safe and it works. Wow, what a revelation. Prior to that, didn't have to. Sort of strange, but... And you'll hear about that again in law and those things. So susceptible types of structure are amides, esters, lactam groups, and proteins, of which a large number of our drug products have these types of groups. This is why you don't see a commercial product of aspirin. You put aspirin, acetylsalicylic acid in water, and it hydrolyzes to salicylic acid in about a week. Remember that 2-year expiration date we were talking about? Nah. Beta-lactams, penicillins typically come, the injectable ones, as powders, and you put them into water right before you use them because they hydrolyze also. So a number of agents, one of the ways to avoid hydrolysis is to not put them in a drug delivery system that has water. So you make a tablet out of it, make a powder out of it. The vast majority of oral anti-infective agents, I try not to call them antibiotics because that actually implies something, but anti-infective agents are powders that you add water to right before dispensing simply because they're not stable for a long period of time as liquids. You can control, limit the hydrolysis. You could use a buffer system. So if there might be a pH at which the reaction is not as fast. Again, we can't stop the reaction, but we can slow it down. You can eliminate water, as I just talked about. You can limit exposure. It might be a tablet, but there's still water in the atmosphere, so you might coat the tablet. That's one of the reasons that some aspirin tablets have a coating on them. It's to make them a little easier to swallow, that's true. But it also makes them a little more stable because water can't get to the aspirin. If there's anything almost as ubiquitous as water, it's oxygen. When you were reading through the history handout, one of the ways they used to state the scientists, pharmacists, that first isolated oxygen. I initially, a few years ago when I wrote that, said they discovered oxygen. I had somebody ask me, well, what did people breathe before oxygen was discovered? I went, good point. Isolated it. It identified it, something along those lines. So oxygen is around. Susceptible structures, again, even some of the same. Culprits are usually molecular oxygen from air. That results in what's termed auto-oxidation, or from free radicals. So those radicals that you pay for don't affect this. They're just the free. Quantity. Double bonds. So carbamazepine can be oxidized fairly readily. Chlorpromazine can also be oxidized. These are just examples. I don't expect you to learn these structures. You will see these structures again at some later point in time. But what this will, hopefully you'll remember, that kind of structure is affected by these types of oxidations or these types of reactions. A lot of these similar reactions occur at the receptor site as well. So it's sort of a beginning of your structure-activity relationships about drug molecules. That's why I throw in some examples. So I'm not going to test you on these. Avoiding oxidation, much like water, you avoid oxygen. Typically don't directly include oxygen in most drug delivery systems, but oxygen is around. So we can coat a solid to block out the oxygen. Interesting thing is putting it into a container to block out the oxygen doesn't work as well as you might think. Glass excludes oxygen pretty well, but most plastics are porous enough that oxygen can go in and out at will. And if you look at the containers for prescription medications, they're almost invariably in something plastic. So that doesn't avoid. So having it in a sealed container doesn't cut it because the oxygen just goes, I can go through there. Oh, now you're going to tell me that oxygen molecules don't talk. Okay. I heard one once. You avoid exposure to it. You can add antioxidants. Is probably the most common. Common antioxidants here. And the first two, if you eat dry cereal of some type, and you look at the ingredients in there and it says BHA and BHT added, those are antioxidants, so your cereal is not oxidized. Butylated hydroxyanisole and butylated hydroxytoluene. BHA and BHT doesn't sound too bad. The long version of it does. Well, it's very small quantities. Ascorbyl palmitate, ascorbic acid, the tocopherols are also antioxidants. Those are in the vitamin E family. So if you see something that has vitamin E added to it, it may not be in there as an active ingredient. It may actually be in there as an antioxidant. So if you look at something and go, why would they put vitamin E in here? So they can charge, may or may not be the case. So what these do is they react with the oxygen more efficiently and faster than the drug will. So it traps the oxygen, so it purposefully reacts with it. Ascorbic acid you'll see a lot. Vitamin C. Dimerization. Reaction of a drug molecule with another molecule of the same drug. So in other words, you got the drug, two of the molecules can react with each other, and when they do, then they no longer have the same properties. They can't be absorbed, they may not even dissolve. Could be a lot of problems with that. So this is an internal kind of issue. Maybe thiol groups, amoxicillin is one that does that. So if it's in solution, it's not just concerned about oxidation here, but it reacting with itself. So you might need to put some, here if you put some antioxidants in it, it might help prevent that, or there may be some other ingredients included to limit the ability of the drug to act with itself.
Would it matter whether it's liquid or
Pardon?
tablet form? The amoxicillin, how it reacted with itself? Would it matter if it had more later?
It has to be in solution in order to form that dimer.
Okay.
So a solid form is more stable because it's not free enough to move to react with itself. I'm sure you'll get a very, very small quantity of that, but not nearly what you would get when it's in solution. Which is why amoxicillin products, even that are liquids, tend to be suspensions because then the amoxicillin is largely not in solution, it's still in a solid form. Isomeric changes could change its optically active form, from the L to the R, etc. Possibly, well, in years past, we would have labs where we could actually measure the L and R forms of certain drugs. Don't tend to do that anymore because it's not cool or clinical or whatever. Remember, I'm a pharmacist, so I can pick on that. But the racemic type of a drug can be important. Who's heard of thalidomide? Who's heard of thalidomide? The bad things about thalidomide. Back in the 60s, it was used in Europe extensively and tried to come into this country as a anti-nauseant for pregnant women. Yet it was found that babies were born with flippers instead of arms and legs. So it was it was not carcinogenic.
Teratogenic.
Teratogenic. Thank you. It was teratogenic. But thalidomide is actually back on the market because it was only the R form, if I remember right, that's teratogenic. The L form is not. So what's on the market now is the L form. So the racemic is exactly the same structure, and I might have those reversed, but
I thought they took it back off because the body converted the L to the R and it was still the same problem.
no, it came back for a while. But it's just one form. It's just the L form that works, and it's only the other form that is teratogenic. Epimerization, geometrical isomerization, structural isomerization. So this can cause just enough change in the molecule, even though the chemical structure of the molecule is the same in terms of its content, its arrangement is slightly different. And what this slightly different arrangement can cause is it not to interact with a receptor either at all or as well. So some drugs, when they were originally produced, were simply a racemic mixture or a mixture of these various and sundry types. Now, with newer technologies, we can identify which form of the drug is more useful. Some of these reactions might occur in the elimination of the drug, in the metabolism or biotransformation of them in the body. So R-epinephrine to S-epinephrine, tetracycline to 4-epitetracycline. And here, if this occurs, this is not nearly as effective against bacteria as the original form. These can occur sometimes in solution or with other ingredients in there, so you would put them in the most stable system possible. Chemical incompatibility, and we're not necessarily always concerned just with drug interacting with excipients, which most people would be careful of. But if you're making a combination drug product, the drugs have the potential to interact with each other. So phenylephrine hydrochloride and aspirin interact together. So you don't tend to see a drug product with those two involved. Or if you're making a dosage form in which both are included, then you might isolate one in a part of the dosage form so they're not in touch with each other. You might see some tablets that are bilayered, and often they may even be different colors. So those two layers are there because there's some interaction between the components in one layer with another, and so to minimize that, they are constructed separately. You have a tablet press, that can compress half the tablet, and then it puts the other ingredient on and compresses the other half. It's an automated process, so you separate out the components. So if something interacts, you don't let it get together. Photo degradation is if you take too much selfies of a tablet or a capsule, then it degrades. If taking too many selfies caused degradation, the Kardashians would have been dead long ago. So photo degradation. No, it's from light energy, from photons. So how that's avoided, and typically we minimize exposure of dosage forms to light, because when you dispense something in a prescription container, what color is it?
It's amber vinyl.
All right, it's amber. So that blocks out the most damaging rays, which are the UV rays, in the wavelengths of about 300 to 500 or so. So we just dispense everything in amber. Most things aren't photosensitive, but for those things that are. And since you don't want to have two different types of containers, I've also seen some green ones which also do the same thing. They block out similar types of things, of wavelengths. So the most damaging in the 300 to 400 nanometer range. And companies, when they're storing things and they're doing stability, this would be part of their protocol. They would have things in clear containers as well as, light-resistant containers to measure. Change in protein conformation. A protein relies upon its three-dimensional structure. So if the environment alters that three-dimensional structure, its effect can be changed quite a bit. It's often related to temperature and excipients. The excipients we can control. The temperature could be an issue, not so much in manufacturing, not so much in storage at the pharmacy level, but what happens in between. How's it shipped? How's it stored? If it's shipped in just a regular truck that's not refrigerated through the plains of Texas over a week, all of your protein could be degraded. It may still have aspects of it there, but its three-dimensional structure is completely ruined. Or it gets to the wholesaler okay, and it sits on the counter from Friday until Monday, and that might be enough to damage it. There are shipping containers with dry ice and labeled refrigerator, freeze right away, etc., etc. And somebody's got to make certain that they actually do that. So stabilizing pharmaceuticals, the goal is to avoid adverse conditions, substances, and or block the adverse condition of substance. Keeping water out of it, keeping oxygen, keeping light, putting it, the container has something to do with it, the other choice of excipients has something to do with it, so a lot factors in to a drug delivery system. Not just what flows easiest or is cheapest to make. You could construct a drug delivery system from fairly inexpensive ingredients, but if your drug is not stable, it's not helpful. Temperature. I can't think of a single instance where the directions for a pharmaceutical product came that said, please store this on the dashboard of your car in the middle of summer. Because that's where it's most stable. Okay, I parked out at Bristol Motor Speedway one time in the summer, and I went back, and when you turn the car on, there's a thermometer in there. It said 130 degrees. Felt like it was 134, actually. That was weak. So usually lower temperatures are better. So you might say, well, let's store everything in the refrigerator. That doesn't work either. Not because of stability of the drug, but the drug delivery system itself. If you store some things, especially suspensions and emulsions, even some solutions, if you store them in the refrigerator and they're not designed for that, you can cause the drug delivery system to fail. So if you have a suspension and you store it in a refrigerator or a freezer or something that's too cold, you can actually cause everything that's in there to fall out of solution and not be redispersible. You can cause your emulsion to unemulsify. It's called cracking or breaking. So if the emulsion cracks or breaks, you can put it on a paint mixer and you're not going to recover it. It won't work. So just putting everything in the refrigerator is not the solution. Just put things in there that are so designed to do that. So the worst place in the house to store medicine is No, there's a worse place. What's the worst place in the house to store medicines? The medicine cabinet in the bathroom. You have increased heat, increased humidity. Worst place in the house. So don't store them there. Simply because you're exposing it to all these bad things that can happen to it. So don't put it there. Put it in some environment that's relatively that you can darken. So you want it in a cabinet somewhere where the temperature is relatively even and where there's not a lot of moisture around. All right. Solvents that might be used in processing and creating a dosage form. If it's subject to hydrolysis, we would want to avoid using water, so we might use a non-aqueous type of solvent. One which, once the product is finished being formulated, that would all be evaporated off and would not be in the final product. That can be challenging sometimes because of toxicity concerns of residuals. So if you're using an otherwise somewhat toxic substance, then you have to be assured that you're removing all of it. You don't want it in the final product. That's why you have to be careful if you're going to use alcohol. Now, by definition, when I say alcohol, I mean ethanol. Because by USP definition, the term alcohol means ethanol. So if I say alcohol, don't say, you mean methanol or propanol or whatever. No, alcohol in the pharmacy arena is ethanol. So if you have to use ethanol, always make certain that the ethanol that you use is not denatured. Denatured alcohol has, like a toxic substance added to it so that it can't be directly consumed because it's a poison. So you do not use denatured alcohol in your pharmacy processing, in your compounding, ever. Because when asked for alcohol, it means non-denatured ethanol. In the lab, we have non-denatured ethanol, and that's what you'll be using. Always use the real stuff when we're there. The only limit is we don't have any controlled substances in the lab. But all the other things that you will be using will be real drug, real reagents, related to how you would do it. Right. Also, don't use absolute alcohol. In other words, that's 100% alcohol, because 100% alcohol is denatured. Interestingly enough. 95% ethanol is the highest concentration that's usable. That other 5% is molecularly bonded water that you can't get out without using a denaturing agent. So if you think, well, 100% would be purer than 95%, no. Don't make that mistake. All right, in terms of pH, we could have a reaction involving in this fashion. Specific acid catalysis, in which the reaction is catalyzed. And remember, a catalytic reaction, the reacting agent doesn't permanently change, so it regenerates. So it's not like we can use it all up, because it's just there. It's kind of like an enzyme. Enzymes are mainly catalysts. So a specific acid catalysis is catalysis by the hydronium ion. So anything that's acidic that has this type of reaction, using some other acidic solution doesn't help that. This is a second order reaction. So if you're using a buffer system to try to stabilize or solubilize something or make it a little more compatible, it's still got a certain hydronium ion concentration, as well as a hydroxyl ion concentration. You had a graph of the rate constant of the reaction of K versus pH. It would yield a straight line with a slope of -1. All right, so K versus pH, and the slope of this, because the slope downward, would be -1. That's a specific acid catalysis. So any acid solution for a drug subject to this type of degradation would cause it to degrade. Specific base catalysis, it's kind of just the opposite. So it's catalysis by the hydroxide ion. It's also a second order reaction. And K versus pH would give a graph that would have a slope of +1, because the pH goes from low to high here. The higher the value of K, the rate constant for the reaction, the faster the reaction. So by changing the pH, we actually change the conditions and change the rate constant. So here, the more basic we become, the less reaction occurs. Here, the more basic we become, the greater the reaction occurs. So these are specific acid and specific base reactions. So any acid environment would cause this to occur. Any basic environment will cause that to occur. Doesn't matter what's creating the environment. Differentiate that from a general acid or general base. Now, I'm not the one that named these. I always thought these were kind of a little bit backwards, but it's what we have to work with. General acid or general base catalysis is one where what's causing the acid or basic system matters. So there's an interaction with the components of the buffer that might be present, or the excipients that are causing it to be an acid or a basic environment. So if it's general acid or general base, it's the drug interacting with those components creating that situation. So what we can do there is you can change components. You can change the buffer system. So if I change, the components of the buffer system in a general acid or general base catalysis, then I can actually minimize or get rid of the catalytic reaction. Whereas in a specific acid-base catalysis, it doesn't matter what the components are, it's simply that pH that matters. So this is a little more preventable because I can simply change the excipient components and make them non-reactive species. So chloramphenicol is one that is degraded by general acid, general base catalysis. And the statement here that some of you are getting up to look at is unlike specific acid or specific base catalysis, because that occurs no matter what's causing, what the components are. General acid, general base, it's reacting with specific components that we can change. We can keep the same pH, different components no longer have the catalytic reaction. A specific acid or specific base, we can change the components and forever, and the reaction's still going to occur at a certain pH. Dealing with oxidative processes, we can flush the container with inert gas. If it's a glass container or a non-permeable plastic, which are fairly expensive to do. But that only works until it's opened. Once it's opened, then it's exposed to the atmosphere. Formulate with as low a pH as possible, because oxidative reactions prefer to react at higher pHs. You can use a chelating agent that binds, at least temporarily, those sites where oxygen would react. So it's tying up the reactive area. We have to be careful that the chelating agent doesn't then inactivate the drug molecule. So it has to be reversible. And if it's reversible, then there's a possibility that oxygen could come in there. Or, of course, use an antioxidant. Questions? I think there have been a few times this semester that I went over a little bit, so here's you 8 minutes back. You didn't even fall asleep.